So this is our conclusion to the topic. We need to check to make sure we've got all of these things completed. If you haven't, contact me and I'll make sure we cover it. So we're looking at gravity in the second column, Newton's law of universal gravitation. We've got that completed. The reason it's called the law is because we believe that it is fact. In other words, it hasn't been disproved and we believe it cannot be disproved. The formula we've used, the variation of gravity as you go further and further away from a massive object, we've done that. The variation of the weight of an object or the force of attraction as you move further away from it, we've done that. The value for the acceleration due to gravity on other bodies in space, such as the moon, we've done that. Compare gravitational forces between the Earth and the Sun and the Earth and the Moon. We should have done textbook questions on that. Calculations done, calculated weight on different planets should be done from the textbook as well. So it's the SDS part we need to keep an eye on. Let's start with the bottom, the presence of atmosphere. So basically, atmosphere is made up of particles. Those particles have a mass. The Earth has a mass as well, and the force of attraction between the particles and the Earth ensures that the atmosphere stays within a particular distance from the Earth, hence keeping us warm and also sustained with oxygen and other useful gases. That one's done. Okay, the solar system. So you should have covered the solar system in the junior cert already. You should really know the relative position of the planets. And what I think you need to know here is the further the planet is away from the sun, the greater the D value in Newton's law of gravitation, so the less or the lower the force of attraction it experiences between it and the sun. A consequence of that is that its circular orbit has a larger radius. The other thing that you'll need to keep an eye on is the more massive the planet, the greater the force of attraction between it and the sun also. And the other thing that I'd mention here are many of those planets have moons themselves, and the force of attraction between the planet and the moons are likewise dependent on the mass of the planet and the moon, as well as the distance between the centres of the planet and the moon. Okay, the last thing then was weightlessness. So let's have a look at it in a bit more detail. And I'm going to get you to do a calculation here so that you're not sitting idly just listening to me. So it's calculate the distance from the Earth where an astronaut will be weightless. So we put the Earth in, we put the moon in, and I should be actually where it's weightless between the Earth and the moon. It should have been said there. So there's going to be a position there where weightlessness is going to occur. And basically what's going to happen is that position there, if an astronaut was present there, the force of attraction between the astronaut and the Earth would be equal to the force of attraction between the astronaut and the moon. We'd have something like that. Now, because they're forces of attraction, we can use Newton's law of gravitation. So those equations will be equal to each other. The small m is the mass of the person in each case, and that will cancel. G is a constant in each case, they'll cancel. And when they do, we'll be left with the mass of the Earth over however far the person is from the centre of the Earth squared, so that's the dE squared, equals the mass of the moon all over however far the person is from the centre of the moon squared. Now, I'm going to get you to do that. What I suggest is finding out how far it is between the centre of the Earth and the centre of the moon. Call the distance between the centre of the Earth and the person, call that distance x, and then the distance from the person to the moon will be the total distance between the Earth and the moon minus x. Fill those into the formula and work it out. And that's your homework.